Dear students, in this video lecture we will study the basics of analog multiplier. An analog multiplier is a device having two input ports and an output port. The signal at the output is the product of the two input signals along with the scaling factor. Here you can see the schematic representation of analog multiplier. Vx and Vy are the two input ports. Vout is the output port. Vout is equal to Vx into Vy divided by K. K is the scaling factor. You can see the definition of multiplier quadrant here. In this table, the first one is the type, that is single quadrant. Vx and Vy are the two input, and Vx is unipolar and Vy is unipolar. Vout is also unipolar. The type is two quadrant multiplier. Here Vx is bipolar and Vy is unipolar. Vout is bipolar. The type is four quadrant. Vx is bipolar and Vy is bipolar, and Vout is also bipolar circuit. And let us see the introduction part. The nonlinear operation on continuous valued analog signals are often required in instrumentation, communication and control system design. These operations include rectification, modulation, demodulation, frequency translation, multiplication and division. In this video lecture, we analyze the most commonly used techniques for performing multiplication within a monolithic integrated circuit. In analog signal processing, the need often arises for a circuit that takes two analog inputs and produces an output proportional to their product. Such circuits are termed analog multipliers. In the following sections, we examine several analog multipliers that depends on the exponential transfer function of bipolar transistors. So let's begin with the topic, the emitter coupled pair as a multiplier. We can use emitter coupled pair as a multiplier circuit. Let us see, the emitter coupled pair produce output currents that were related to the differential input voltage by IC1 is equal to IEE divided by 1 plus exponential minus VID by VT, and IC2 is equal to IEE divided by 1 plus exponential VID by VT. And delta IC is equal to the difference between these two input currents, collector currents, that is delta IC is equal to IC1 minus IC2, that is IEE into tan H of VID by 2VT. This relationship is plotted and shows that the emitter coupled pair by itself can be used as a primitive multiplier, or assuming VID by 2VT much less than or equal to 1, that is delta IC is equal to IEE into VID by 2VT. The current IEE is actually the bias current for the emitter coupled pair. With the addition of more circuitry, we can make IEE proportional to a second input signal. Thus, we have IEE approximately equal to K0 into Vi2 minus VBE on. The differential output current of the two emitter coupled pair can be calculated to give delta IC approximately equal to K0 into VID into Vi2 minus VBE on divided by 2VT. And what are the two quadrant restrictions? Thus, we have produced a circuit that functions as a multiplier under the assumptions that VID is small and that Vi2 is greater than VBE on. The latter restrictions means that the multiplier function in only two quadrants of the VID minus Vi2 plane, and this type of circuit is termed a two quadrant multiplier. The restriction of two quadrants of operation is a severe one for many communications applications, and most practical multiplier allows four quadrant operation. The Gilbert multiplier cell shown is a modification of the emitter coupled cell which allows four quadrant multiplication. And why we are going for this Gilbert multiplier cell? There are various methods available for performing analog multiplier or multiplication process. Just now we have seen that emitter coupled multiplier cell. In similar way, you can use log amplifier multipliers, but there are some disadvantages in these type of multipliers. Then why we go for this Gilbert multiplier cells? The disadvantages of these type of multiplication are the very limited bandwidth and the single quadrant operation. A far better type of multiplier uses the Gilberts cell, This structure was invented by Barry Gilbert in the late 1960s. So let's begin with the topic Gilbert multiplier cell. The Gilbert multiplier cell is the basis for most integrated circuit balanced multiplier systems. The series connection of an emitter coupled pair with two cross-coupled emitter coupled pairs, produces a particularly useful transfer characteristics. So this consists of an emitter coupled pair with two cross-coupled emitter coupled pairs, and let us see the various currents, output currents, collector currents. IC3 is equal to IC1 divided by 1 plus exponential minus V1 by Vt. IC4 is equal to IC1 divided by 1 plus exponential V1 by Vt. IC5 is equal to IC2 divided by 1 plus exponential V1 by Vt. IC6 is equal to IC2 divided by 1 plus exponential minus V1 by Vt. And here is the Gilberts Cell DC analysis. The two currents IC1 and IC2 are related to V2, and we have already seen that IC1 and IC2 equations, and substituting IC1 and IC2 in expression 4, IC3, IC4, IC5 and IC6, will get IC3 is equal to IEE divided by 1 plus exponential minus V1 by Vt into 1 plus exponential minus V2 by Vt. IC4 is equal to IEE divided by 1 plus exponential V1 by Vt into 1 plus exponential minus V2 by Vt. And IC5 is equal to IEE divided by 1 plus exponential V1 by Vt into 1 plus exponential V2 by Vt. And the final IC6 is equal to IEE divided by 1 plus exponential minus V1 by Vt into 1 plus exponential V2 by Vt. And the differential output current is given by delta I is equal to IC3 minus I5 minus IC4 to I6. That is IEE tan H V1 by 2 Vt into tan H V2 by 2 Vt. That is IEE tan H V1 by 2 Vt into tan H V2 by 2 Vt. And if V1 much less than Vt and V2 less than Vt, then tan H V1 2 by 2 Vt approximately V1 2 by 2 Vt, and it works as multiplier. If one of the inputs of the signal that is large compared to Vt, this effectively multiplies the applied small signal by a square wave and act as a modulator. Gilberts cell as a multiplier. You can see the equation. If V1 much less than Vt and V2 less than Vt, then tan H of x is equal to x plus x cube by 3, etc. Thus, for small amplitude signals, the circuit performs an analog multiplication. Unfortunately, the amplitudes of the input signals are often much larger than Vt. An alternate approach is to introduce a nonlinearity that pre-distorts the input signals to compensate for the hyperbolic tangent transfer characteristics of the basic cell. The required nonlinearity is an inverse hyperbolic tangent characteristics. And complete analog multiplier circuit. This is a complete analog multiplier circuit, and we will get V out is equal to IEE into K3, K1 by I naught 1, K2 divided by I naught 2 into V1, V2 is equal to 0.1 V1, V2. This is the final output voltage equation for analog multiplier circuit. Thank you.